find the summation. Another way to say this is evaluate the summation. In the first summation here, we have I going from 1 to 38 of I cubed over 4. So when we find a summation, what we're trying to do is make sure that there are only i's left inside the summation, because the four formulas that you know help you sum a constant, I squared, or I cubed. So when we look at the argument of this summation, this divide by 4 is messing up our chance to use the formula for the sum of I cubed. So we can use the constant multiple rule to pull that 1/4 constant to the front of the sum. So you'll be left with 1/4, the sum as I goes from 1 to 38 of I cubed. So now that we have I cubed only left inside the argument, we can use the summation formula for I cubed. And the summation formula for I cubed states that you have the upper bound, that 38, squared, times the upper bound plus 1, that'll be 39, squared, all over 4. And I wrote this and didn't say it. We still have to multiply this sum by the 1/4. It comes along for the ride. So there it is. And when you compute all this out, you'll get these answers right here. You'll either get this 549,081 over 4, or if you divide it out, 137,270.25. In this next example, we have the sum as I goes from 1 to 17 of 4i times the quantity I minus 2. And when we're trying to find these sums, we have 0 formulas for the product of i's. So what we need to do is we need to distribute this 4i to each term inside the binomial to get a sum that looks something like this. The sum as I goes from 1 to 17 of 4i squared minus 8i. So we are summing up this binomial now. Except again, we don't have a formula that states what the sum as I goes from 1 to n of 4i squared minus 8i. All we know is that a sum of I squared, and we can find the sum of I, or a constant, or I cubed. So we need to use the constant multiple rule like we did in this other example. This 1/4 came out to the front. So we'll be able to do that here with the 4 and the 8, but now we can use the sum and difference rule to spread out the sum of each term as well. So this will look like 4 times the sum as I goes from 1 to 17 of I squared minus 8 times the sum as I goes from 1 to 17 of I. So we can take the sum of each term individually and then pass the constant through the sum so that we can have our sums in terms of i's and I squareds. So from here, we can say that this equals 4 times, when you use the upper bound in the formula for I squared, you'll have 17 times 18 times 35. Right, this is the upper bound times the upper bound plus 1 times 2 times the upper bound plus 1, all over 6. From that, we are subtracting 8 times the summation of I from 1 to 17. The upper bound again is 17. So the summation of I from 1 to 17 is the upper bound times the upper bound plus 1, all over 2. And when you compute all this out, you'll get 5,916 for your summation answer. So the takeaway from these two examples are the use of the constant multiple rule. This I cubed is being multiplied by 1/4. So we can common factor that out of the summation. And in this other example, we have the fact that you need to multiply. Everything needs to be addition or subtraction. There cannot be any terms being multiplied to anything else. And then from there, we can use the sum and difference rule to separate out each term into their own sum, and then use that constant multiple rule. That's 8 times I. The 8 got common factored out of this one, and the 4 got common factored out of this one.